In the previous episode, I showed how to calculate which station parameters can be used to bridge a distance with a 6 cm transmitter. Whether the transmitted signal is omnidirectional or with a directional antenna, between the transmitting antenna and receiving antenna, the signal that uses the ether is always cigar shaped. This is called the Fresnel zone. The diameter of the Fresnel zone depends on the frequency and the distance. At a higher frequency, the diameter of the Fresnel zone is smaller. If 60% of the cigar diameter arrives at the receiver, there is only little extra attenuation compared to the unblocked path damping. Then the calculator described in episode 1 is valid. However, if the Fresnel zone is covered more than 60%, the losses increase rapidly. An example with the horizon: a location has been chosen close to the ground and the antennas can just see each other. Then half of the Fresnel zone, 50%, is covered and there is no guarantee that the contact will happen. One of the antennas or both should then be placed higher to have the Fresnel zone sufficiently clear. That is also the reason that talkback over a few kilometers between handhelds could be difficult, while a repeater much further away could be used without any problem. In both cases the antennas see each other, but in one case the Fresnel zone is covered and the other situation not. To calculate the obstruction of a Fresnel zone, also a web calculator is available. The link is mentioned below. First, select the wanted units. I like kilometers. Frequency, suppose 5780 MHz. K-factor, we leave it 1.33. I will come back later on that. We leave also the percentage and, why not, the link distance. And we place both antennas at the height of 1 meter. In the output we see the radius of 60% of the Fresnel zone, in this case 9.7 meters. The minimum clearance point is at 10 kilometers, logically exactly between both antennas. The clearance value is negative. This means that the Fresnel zone is completely blocked. The contact will not happen. Raising the antenna on one side shows that the horizon will shift and the antenna must be very high to pass the Fresnel zone over it. Or both antennas could be placed higher. Change frequency to the 2 meter band and you see that the diameter of the Fresnel zone will increase. And in this example the antennas need to be raised further for this lower frequency for Fresnel clearance. I change the frequency back. In case of a known obstruction, like a hill or a large building, it could be keyed in here. Depending on the height and distance of that obstruction, it has more or less influence on the blocking of the Fresnel zone. You can play with that. Back on the K-factor. RF signals travel more or less in a straight line in space. However, regular refraction bends signals often slightly toward Earth, allowing them to travel beyond the optical horizon. Temperature and air pressure at different altitudes are responsible for this. This is expressed in the K-factor. More on this in a later episode that you will be made aware of if you subscribe. See you!